Hello dear friends, this is Dr. Diptesh Patel and welcome back to the online video lecture series of Jet Propulsion and Aircraft Engineering. This is lecture number 13 of Principles of Jet Propulsions, and in this video session we are going to see another numerical which is very important in terms of GTU exam, because these are the numerical which has already been asked in the exam for 7 marks. So the outline of this video session is numerical number 7. So here is the numerical. It says that an aircraft powered by a pulse jet engine which is flying at 12 km altitude. So here in this numerical we have to solve an example on the basis of pulse jet engine, which is the first time we are doing here, right? So here the pulse jet which is flying at 12 km altitude. So the height of the aircraft from the ground is 12 km, and the speed is at Mach number 2. So the Mach number for the pulse jet engine or the aircraft is 2. Furthermore, the engine parameters which are also given, and those are the inlet area, that is 0.084 meter square, the combustion chamber pressure development or the pressure ratio, that is PO3 to PO2, and that one is 9. So the pressure ratio in combustion chamber is 9. Then calorific value of fuel, and that is 43,000 kilojoule per kilogram. Then combustion efficiency or the combustion chamber efficiency, eta C, that is 0.96. Here we are making an assumption. It says there is an ideal flow through the intake, so there is no any losses takes place into the intake of the pulse jet engine. Now with the given value we need to calculate, these are the different things. The first one is air mass flow rate, second one is a maximum temperature, third one is a fuel air ratio, fourth one is the exit velocity of the aircraft, fifth one is a thrust of the engine that can be achieved in the pulse jet. Then TFSC, thrust specific fuel consumption, which is the sixth finding that we need, and the last one is a propulsive efficiency, eta P. So here we need to find out the 7 different values. Now according to GTU, that example was asked for 7 marks, so you will probably get a 1 mark for each finding, and here we need to go through the 7 different ones. So let's start the numerical. Since the altitude of the craft or the pulse jet is given, and that is 12 kilometers, so on the basis of that altitude we can get the inlet conditions of the air which is entering into the diffuser. Furthermore, since it is a diffuser, so we are going to have the pressure buildup, maximum pressure buildup in diffuser. So let's say POA, which is the pressure of inlet air, and that is 18.75 kilopascal. So the air which is entering into the diffuser has the pressure 18.75 kilopascal. Then temperature of the inlet air, that is TOA, and that is 216.65 Kelvin. Since on the basis of that I should be able to get the flight velocity, right? We know that Mach number, which is equal to the object velocity divided by sound velocity. So we are going to use the same formula to calculate the object velocity or the flight velocity. So let's say VA, which is equal to MA into omega under root of gamma RTA. Since we know that under root of gamma RTA is the velocity of sound, so we are going to substitute the values, and on the basis of that substitution we calculate the flight velocity, which is 590 meter per second. So this is the flight velocity, 590 meter per second. Then after, the next one is the air mass flow rate, okay, which is equal to rho A VA into A1. Okay, so since the density VA which we have calculated and the area that is given. So substituting the values, I should be able to get the air mass flow rate, which is also known as MA, the mass or amount of air which is entering into the diffuser, and that is 15 kilogram per second. So on the basis of that, I should be able to say that the amount of air which is entering into the pulse jet, which is 15 kilogram per second. Then after, let's move forward to the next finding. Here we know that the total temperature across the inlet of the diffuser, that is remain constant, because that was the assumption that we have made when we start the examples. So since the temperature is remain constant, I should be able to say TO1 is equal to TO2. So therefore TO1, which is equal to TOA inside the bracket Ta into 1 plus gamma minus 1 into m square divided by 2. So after substituting the values, I should be able to get TO1, which is equal to 390 Kelvin, and that is equal to TO2 because the pressure, the temperature is remain constant. Then after, the total pressure. Now total pressure PO1 is equal to POA, which is equal to PA inside the bracket TO1 upon TOA raised to gamma upon gamma minus 1. So this is the isentropic relations that we are going to use to calculate the pressure at the outlet of the diffusers. And once you substitute the values, you should be able to get PO1, which is equal to 147 kilopascal. So here we are keeping all the units same. So here we are using the kilopascal. Then move forward to the combustion delivery temperature. So after combustion, what would be the temperature of the whole cycle? And we know that that is the highest temperature that can be achieved. So here in the combustion chamber, the pressure is rising from P02 to P03, and that is described by the pressure pressure ratio, and that is given 9, right? And the temperature ratio is also same by the gas law. So we can calculate the combustion delivery temperature, and that is equal to T03 is equal to 3510 Kelvin, 3510 Kelvin, which is the obviously the highest temperature that can be achieved. Then fuel ratio. The fuel ratio can be calculated as MF upon MA. So we are going to denote the fuel ratio, which is equal to small f, which is equal to MF upon MA. Therefore, I should be able to write down, since we know that MF, which is equal to Cp gas T03 minus Cp air T02, specific heat of gas and specific heat of air, divided by Q into efficiency of combustion chamber eta Cc. Substituting the values, I'll get the fuel air ratio, and that is equal to 0.0975. So that is the fuel ratio, and this is our next finding. Then after, let's calculate the exhaust velocity. Right? So the exhaust velocity, which is the velocity of gases which are leaving the nozzles, right? So we need to calculate the jet pipe exhaust velocity by using the formula called VE is equal to under root of 2 Cp gas, specific heat of gas, into T3 into 1 minus 1 upon 9 raised to 0.25. So substituting the values would help us to get it, and that is 2297 meter per second. So that is the exhaust velocity in the nozzle. Then a specific thrust. Since we know that specific thrust F is equal to specific thrust is equal to F upon ma, right? So therefore I'll get the equations called 1 plus F into VE upon VE minus VA. Now we got all those value. We already calculate these value. V is a exhaust velocity, VA is a velocity of aircraft, and F is a fuel ratio, fuel air ratio. So Once we put the values here, we'll get the specific thrust, and which is equal to 1931.5 Newton second per kilogram. Then after, the next thing is a thrust. So on the basis of that, we can calculate the thrust, which is capital F, that is equal to 28,950 Newton, or I should write 28.95 kilonewton. So that is the thrust that can be achieved. Then the thrust specific fuel consumptions, and to get the thrust specific fuel consumption, I'll use the equations called F upon capital F plus ma divided by 50 divided by ma. So doing the substitution, we'll get the specific fuel consumption, thrust specific fuel consumption, which is equal to 50 milligram per Newton second, and that is equal to 0.180 kilogram per Newton per hour. So we just change the unit here from milligram to kilogram and then second to hour. So this is the thrust specific fuel consumption. This fuel consumption takes place per unit thrust per unit time. And the last finding is a propulsive efficiency, and the propulsive efficiency eta p is equal to F into Va divided by F into Va plus 1 divided by 2 m dot inside the bracket 1 plus F into Ve square minus Va square. So after putting the values here, since we got all of them, we would be able to find out the eta p, which is equal to 0.418, and after conversion in percentage, that would become 41.8 percentage. So this is the values of propulsive efficiency of the pulse jet engine. Okay, so this is all. These all finding would help us to get the 7 marks. Now these examples are important because this has been already asked in GTU exam in previous one. So make sure you would go through it. Now if you have any doubt, you can write down in the comment box regarding the numerical. Thank you very much.